Our next example of uninhibited exponential decay is Newton's law of cooling. So Newton's law of cooling states that the temperature of a heated object decreases exponentially over time towards the temperature of the surrounding medium. And this is an example of exponential decay. Now this statement makes sense, right? You take something out of the oven, you leave it on the counter, it's eventually going to cool down to room temp, right? Same thing is true with your coffee, which is depressing, right? It'd be nice if it stayed hot all day. But Newton's law of cooling is this: the temperature U of a heated object at a given time can be modeled by the following function. U of t equals T, which is the constant temperature, so that's like your room temperature, plus U naught, which is the initial temperature, minus T, times e to the kt, where k is a negative constant and t is our time. So here's an example of what exponential decay or cooling looks like. So why don't we go ahead and work through an example as I take a sip of my very cold coffee. So let's talk about Newton's law of cooking. Cooling. I'm so punny. This is what you signed up for. So let's say a cake is heated to 350 degrees Fahrenheit and then allowed to cool in a room whose air temperature is 70. If the temperature of the cake is 300 degrees Fahrenheit after 5 minutes, so U of 5 is 300, when will its temperature be 200? So the first thing I'm going to do is I'm going to use this information to solve for k. I have that U of t equals 70. That's my temperature of the surrounding medium, plus 350, that's the initial temperature, minus 70 e to the kt. Well, I know this will simplify to U of t equals 70 plus 280 e to the kt. And I have some information. I know that U of 5 is 300 degrees Fahrenheit. So I have 300 equals 70 plus 280 e to the k times 5. So I subtract 70 from both sides, and I get that 230 equals 280 e to the k, 5k. I divide both sides by 280. That gives me 230 over 280 equals e to the 5k, and I take the natural log of both sides, and then we have to go up here because I'm out of space. So I'm going to have the natural log of 230 over 280 equals the natural log of e to the 5k. We move the 5k to the front. So that's just going to equal 5k. We go ahead and divide both sides by 5, which means k is about negative 0.039342. I can now substitute this in to my original equation. So let me give everybody a second to copy this down, and then I'm going to rewrite my new equation. All right, so now I have U of t equals 70 plus 280 e to the negative 0.039342. I don't know why I kept so many decimals on the exam. I'll tell you how many decimal places to round to. Probably not 7 like I have here. Nope, 6. Can't count. 6 to the t. Now, I want to know after how long will my temperature be 200. So I want to know 200 equals U of what? So I have 200 equals 70 plus 280 e to the negative 0.039342 t. Well, I go ahead and I subtract 70 from both sides. That gives me 130 equals 280 e to the negative 0.039342 t. I divide both sides by 280 to get that e all by itself, because it has to be all by itself before I can take the natural log of both sides. Let me clear myself a little more room. If I have 130 over 100 over 280, right? This is where we're going to. That equals e to the negative 0.039342t. I go ahead and take the natural log of both sides. So I have the natural log of 130 over 280 equals, this comes to the front, the natural log of e cancels, negative 0.039342t. And I divide both sides by this constant. That gives me t is about 19.5 minutes because my time is in minutes. So here's the problem all solved out. Again, not with parentheses or equal signs, but you can look at the homework. You can look at the PowerPoint on Blackboard and see all of these things. So let's say this cake is heated to 350 degrees and then isn't allowed to cool in a room temperature whose temperature is 70 degrees. What if I want to determine the amount of elapsed time before my cake is 100 degrees? So I still have the same equation, which we found was u of t equals 70 plus 280 e to the negative 0.039342 t. Okay, so I'm gonna start this by setting, I want to know when u of t equals 100. So I'm going to take 100 equals 70 plus 280 e to the negative 0.039342 t. I subtract 70 from both sides, and I get 30 equals 280 e to the negative 0.003942 t, and I divide both sides by 280. This gives me 330 over 280 equals e to the negative 0.003942 t, and I take the natural log of both sides. So I have that the natural log of 30 over 280 equals e to the negative 0.0, I don't know where I got that extra zero, sorry, 0.03942 t, and I take the natural log of both, oh, I already did that. Okay, so I took the natural log of both sides. That gives me that this side equals negative 0.0394342 t. And I divide both sides by this constant. And that equals, that's going to give me that t equals about 56.8, oh, we changed colors, I don't know why, 56.8 minutes. Let's try this again and think about, so what do we notice about the temperature as time passes? So as T increases, our temperature decreases, which if you think about cooking or waiting for your food to cool so you don't burn your tongue, is a concept that should make sense to us. So again, I have the answers all written out in the PowerPoint. Okay, so I have u of t equals 70 minus plus. I just wanted to go ahead and fill in the symbols that were missing. So everyone's on the same page, especially if you are watching this online and are not in my course and did not get the PowerPoint. It might be good for you to have. Keep in mind that this is a negative, but it dropped a negative symbol.